page here is a list of stuff. And you don't need to write down the list of stuff at the top of the page here. But the stuff up at the top of the page represents things that I think you have learned how to manage over the course of the semester. So we've got balanced equations. But if you think about it, just to write a balanced equation, you had to learn a whole lot of different stuff. You had to learn how to write chemical formulas. You had to learn the naming conventions to get from names to chemical formulas. You had to learn the charges on the ions so you could get them balanced out. You had to learn your polyatomic ions, and you had to learn how to balance a chemical equation. So just that one little task has quite a lot of things bundled up in it. We have learned about density. We've learned to use your periodic table to look up a whole bunch of different stuff. You've learned about chemistry's magic number, 6.022 times 10 to the 23rd. You've learned about the ideal gas law, PV equals nRT. You've learned about molarity. We talked on Friday about limiting reactants. We've learned about gases occupying 22.4 liters of space per mole at STP. We've learned how to calculate molar masses. And in the middle of all of this is this idea that we can go from moles of A to moles of B. So right in the middle of your page, I want you to put moles of A to moles of B. The connection between moles of A and moles of B comes via the balanced chemical equation. But we've recently learned that when we use the balanced equation to relate moles of A to moles of B, that we have to think about whether we have a limiting reactant. Are we going to run out of something along the way? Now this moles of A to moles of B was built originally because we had learned in the very beginning of talking about balanced equations that the balanced chemical equation was a way to connect particles of A to particles of B. And then partway through Unit 2, we learned that sometimes the best way to count the particles isn't to count them in terms of exactly how many, but to count them in terms of chemistry's counting number, which is the mole. And so we learned that particles of A were connected to moles of A via 6.022 times 10 to the 23rd, and that particles of B and moles of B were also connected via 6.022 times 10 to the 23rd. And whether we thought about particles of A and particles of B, or moles of A and moles of B, just kind of depended upon the information and the way it was given to us. After talking about limiting reactants, you can probably now envision that if you're going to move between particles of A and particles of B using your balanced chemical equation, that just like when using moles of A and moles of B, you're going to have to consider the possibility that you do in fact have a limiting reactant. In our early conversations about stoichiometry, however, we learned that it's fairly rare to be given your amounts in terms of moles, and it's fairly rare to be given your amounts in terms of particles, but because of the way we work and measure things in lab, you are much more likely to be given your amount of substance A in terms of grams. But that wasn't that big of a deal. We knew that using the molar mass, which we could find on the periodic table, it was pretty easy to convert grams of A into moles of A and then be ready to use our balanced equation to get to moles of B. And on the flip side, we could do exactly the same thing. If the problem asked for an answer in terms of grams, after we got to moles of B, we could use the molar mass which we could find on the periodic table in order to figure out how many grams of B we had in the very end. And so we built kind of this central theme for our simplest stoichiometry problems, which involved going from grams of A to moles of A to moles of B to grams of B. And then we started tying our stoichiometry into a lot of other things that we already knew. For example, if A happened to be a pure compound or a pure element, sometimes working with pure compounds or elements, we know an amount in terms of milliliters. But our connection point between milliliters of a pure compound or a pure element is density, so we could use the density in order to go from milliliters of A to grams of A, and then we could convert into moles, and we were ready to go again. Just like getting back to grams, getting back to milliliters can happen on the other side as well. Once you make it all the way to grams of B, if the problem requests that you give an answer in terms of milliliters, all we've got to do is look up the density of B, and we can get ourselves back to milliliters at that point as well. And now we have to consider some other possibilities here. The next possibility we're going to consider is, what if A is a gas? If A is a gas, gases have kind of this interesting triangular relationship between the pressure, the moles, and the volume. And if you know any two of those, the third one becomes quite readily accessible. The link being our ideal gas law. And sometimes, when you're working with gases, you'll get fortunate enough that the gas will actually be at standard temperature and pressure, or STP, and you end up not having to use PV equals nRT, but can instead use the shortcut of knowing that 22.4 liters of gas represents 1 mole of gas at standard temperature and pressure. And as always, the right side of this diagram looks just like the left side of the diagram. Once you get to moles of B, you can report that in terms of the pressure that gas B is exerting, in terms of the volume that gas B occupies, or the volume that gas B occupies at standard temperature and pressure. Now we need to go back up and get the PV equals nRTs and the 22.4 liters per mole. So we'll go up and grab those, put them where they belong. So again, our connection between pressure and volume and number of moles is our ideal gas law, or at STP, this 22.4 liters being equivalent to 1 mole of gas. As long as we're on the topic of gases here, we need to consider one more possible shortcut. If we happen to have substance A being a gas and substance B being a gas, there's going to be a shortcut to let us traverse from liters of gas A to liters of gas B directly, much like up at the top, we could go from particles of A to particles of B without having to come through moles. Down at the bottom here, you're going to be able to go from liters of gas A to liters of gas B without having to come back through moles, because in getting from liters of gas A to moles, you're going to multiply by one number, use your balanced equation, and then you're going to divide by the same number. And so in the end, we're going to be able to sort of cut a shortcut across the middle there, just using our balanced equation. Of course, checking to see if we have a limiting reactant. So the ratio of the coefficients in the balanced equation not only gives a mole-to-mole ratio and a particle-to-particle ratio, but if the two things you are comparing happen to both be gases, that ratio from the balanced chemical equation is going to give us a liters-to-liters ratio between the gases as well. The last possibility we have are solutions. If substance A has been dissolved into water, it's possible that our amount of A might be given as liters of solution. And we know that the connection between liters of solution and moles of the substance that's been dissolved in it is going to be our molarity, because molarity is moles per liter. And it's possible that in the end, we will want to know how many liters of solution B we have. So after you find your moles of B, you can use your molarity of solution B to get back to liters of solution B. Unlike the particles of A and particles of B, moles of A and moles of B, liters of A and liters of B, there isn't a shortcut between liters of solution A and liters of solution B. And it's because these two values, the molarities, are not necessarily going to be the same, whereas the conversion factor from liters to moles and moles back to liters was the same for A and B. And the conversion factor from particles back to moles and particles, or moles back to particles, was the same for A and B. This molarity isn't necessarily the same for both of them, and as a result, we don't have a shortcut to get from liters of A to liters of B. We have to actually travel through the moles with that one. Once you understand all of the parts and pieces of this chart, all the parts and pieces here are things that you've learned, solving chemistry problems ends up being as simple as putting your finger on the box you start with, putting your finger on the box you finish with, and building a plan by following the arrows to get from where you are to where you need to be.